All right, let's jump right in. Today, we're going to crack the code on a really powerful tool in multivariable calculus. We're going to move beyond the nice flat world of the xy plane and see how calculus actually works on surfaces that curve and bend in 3D space.
Okay, so let's get our bearings here. By now, you're all pros at using double integrals, right? If you've got a flat rectangle or a disk and you need to find its mass, or maybe the volume of a cylinder above it, the double integral is your go-to. We've got that covered. But let's be honest, the real world isn't flat. So what happens when you need to calculate something over a curved surface, like the dome of a building or the side of a satellite dish? Well, that's the big question we're going to tackle today.
And that's our whole goal here, to step off that flat plane and start working in the world of complex curved surfaces. This is really where calculus starts to get incredibly interesting and way more useful for describing real-world things.
So let me introduce the hero of our story today, the surface integral. The best way to think about it is like a double integral's bigger, more powerful sibling. It's designed specifically to add up or accumulate some kind of scalar quantity. We're talking things like mass or temperature or electric charge that's spread out all over a curved surface, which we'll call S. Now that formula might look a little intense at first glance, but don't worry, we're going to break it all down.
And actually, this leads to a really cool and simple idea. What if that function you're integrating, f of x, y, z, is just the number 1? Well, then you're not really weighting any part of the surface. You're just adding up all the tiny little patches of the surface itself. And what do you get when you add up all the little pieces of a surface? You get its total surface area. This is a super useful special case to keep in your back pocket. So we know what a surface integral is, but the big question is, how do we actually solve one? Well, it turns out there's this fantastic, reliable recipe that turns these really complex-looking problems into a totally manageable step-by-step process. And this right here, this is the core of everything we're doing today. Just 3 steps. First, we parameterize the surface. This is just a fancy way of saying we're going to describe our 3D curved surface using only 2 variables, u and v. Think of it like taking a flat, stretchy piece of graph paper and perfectly wrapping it onto, say, a basketball. Step 2, we calculate the area element, ds. That term, RU cross RV magnitude, that's our stretching factor. It tells us exactly how much a tiny square on our flat graph paper gets stretched and distorted when it lands on the curved surface. And finally, step 3, we use these pieces to rewrite the whole thing as a standard double integral over our nice flat UV grid. And that's a problem we already know how to solve.
Now, this recipe isn't just some abstract theory. It really does work. And the best way to get a feel for it is to just see it in action. So let's walk through an example together.
All right, here's our first problem. We've got a simple tilted plane, nothing too crazy, given by z equals 1 plus x plus y. And we're only looking at the piece of it that's floating above a 1 by 1 square on the floor, the xy plane. Now, here's the twist. Its density isn't the same everywhere. The density is equal to its height, z. So the higher up the ramp you go, the denser and heavier it gets. Our job is to find the total mass. Let's just follow our recipe. Step 1, parameterize. This is about as easy as it gets because z is already a function of x and y. So we'll just let x equal u and y equal v. Simple. Step 2, calculate that stretching factor. We take the partial derivatives of our parameterization, find their cross product, and we get the vector -1, -1, 1. The magnitude or length of that vector is the square root of 3. What this tells us is that every little piece of our flat domain gets stretched by a constant factor of root 3 when it's on the tilted plane. Okay, step 3, set up the integral. We swap out our density function z for its parameterized version, which is 1 plus u plus v, and we swap out ds for what we just found, root 3 du dv. And look at that, it's just a standard double integral now. You go ahead and crunch those numbers, and you find that the total mass of that surface is exactly 2 times the square root of 3. See? The recipe took a tricky concept and made it totally straightforward. Okay, that was a flat surface, kind of like a warm-up. Let's try something with some actual curves to it. This time, we want to find the surface area of a bowl shape, a paraboloid, but only the part of it that's below the height z equals 4. And remember, since we're after surface area, this is that awesome special case where our function f is just 1. Now, the shadow this bowl casts on the xy plane is a circle with a radius of 2. That right there is a huge clue that we should probably use polar coordinates to parameterize it. So we do that, we calculate our new stretching factor, ds, and then we set up our integral. And check this out. Notice how we have an r sitting outside the square root and an r squared inside?
That is a classic textbook setup for a U substitution. It's practically screaming at us to use one.
Okay, I want to pause here for a second because this is so important, and it's honestly one of the most common mistakes people make in calculus courses. When you switch your variable from R to U using a U sub, you have to remember to change your integration bounds to match that new variable. If you forget this step, you can do everything else perfectly, and your heart work will still lead you to the wrong answer. So please, don't forget the bounds. And after we correctly do that U substitution and change our bounds and integrate, we get our final answer. Yeah, it looks a little messy, I'll give you that, but that is the exact surface area of that piece of the paraboloid. The process was a little more involved for sure, but our recipe still worked perfectly.
So we've seen how to follow the recipe and get the right answers, which is great for an exam. But let's zoom out for a second. What's the big picture? Beyond the classroom, why is this mathematical tool even important? Well, these applications are absolutely fundamental to physics and engineering. You want to calculate the mass of a curved airplane wing where the material's thickness changes? You need a surface integral. You want to find the total electric charge sitting on a weirdly shaped conductor? Surface integral. Or figure out how much heat is flowing through a boundary? You guessed it. This isn't just abstract math. It's literally the language we use to describe and measure the physical world around us. And that kind of leads us to a final, pretty interesting question to think about. We now have this incredible tool to add up quantities that are living on a surface. But what if we wanted to measure something passing through that surface? Like the amount of water flowing through a net or the strength of a magnetic field passing through a loop of wire. Well, that's a whole different kind of problem, and it perfectly sets the stage for our next big adventure in vector calculus. Thanks for tuning in.